Ms. Samira for the introduction. My pleasure to be here today, and thanks for the organizers of this meeting for the invitation to be here. I really appreciate the invitation. It's my honor to be here. Also, I would like to thank all of you online attending this meeting and attending my talk. So you can see in the slide on the screen the title of my talk today. So it has to do about nanocomposites and the use of radiofrequency therapy for modulating in cancer therapy. So here is my agenda for today. I will present to you. Actually, my talk has to do not only with the presentation of nanocomposites and radiofrequency, but also it has to do with some in vitro assays, and therefore, to understand better the in vitro results, I will be using a mathematical model. And so I will present to you some interesting aspects about math modeling for in vitro assays. And I will take the chance to show you the typical in vitro data presentation you can see these days in the literature with no mathematical model. And then I will switch to describe to the radio frequency therapy and presentation of the nanocomposite, which is a graphene oxide-based nanocomposite. And then I will show you the design of the in vitro experiment we performed. And then finally, I will analyze the in vitro data using a mathematical model based on the Hill model, and then I will come at the end with my conclusions. And therefore, afterwards, the session will be open for questions. I'll be happy to take the questions. So, if you take your time to do a little search about in vitro assays, we will find that a small fraction of the data, less than 1% of the data, in vitro data, and there is a huge number of publication in Web of Science, for instance. It's close to 3 billion papers, including in vitro assays, but only a small fraction includes any mathematical modeling. You may wonder why is so small fraction. Because the big challenge is to move from a qualitative description to a quantitative description. Of course, to jump from one step to the next one, it requires basically two important ingredients. First is to be able to use and manipulate a mathematical model. And that requires some basic background in math. The second aspect is to use a model, let's say one analytical expression, to fit the experimental data. However, we have this tool for a few centuries, which is called the least square fitting procedure. So it was actually proposed in the 18th century by the brilliant German mathematician Gauss. So we have actually these days, we have all the tools to implement a more quantitative analysis of in vitro data. Nevertheless, the number of papers published in Web of Science, for instance, which is a very important platform, is less than 1%. And however, If you look at in the last 2 decades, the number of papers, including a mathematical model in vitro papers, has grown systematically, which is a very good point to emphasize. So actually, it triplicates in the last 2 decades, which give us a hope that in the future, researchers will use more and more a mathematical analysis, which has a huge benefit, actually. So let me show you a typical in vitro data presentation. If you go in the literature, you can find this. This is the dominant presentation of the data. I just took one paper from last year. So in this paper, what they do, they are testing two different cell lines, the T24 and the EJ cell lines. Both are cancer cell lines, and they are testing a chemotherapeutic agent. So echinotine is a chemotherapeutic agent. So they are testing the cell viability of these two cell lines, challenged by these chemotherapeutic agent. And you can see on the left-hand side, so the cell viability just reduces as one increases the concentration of the chemotherapeutic. And the tests were performed 24 hours incubation, 48 hours incubation, and 72 hours incubation. Likewise, you can see on the right-hand side, the EJ cell line tested also using the same chemotherapeutic agent, and you see the systematic reduction of the cell viability as you increase the concentration of the drug. And again, the assay, this in vitro assay, it was performed 24 hours incubation, 48 hours incubation, 72 hours incubation. So what we can extract from these two experiments? So we can extract some information, of course. For instance, as you increase the concentration of the chemotherapy, the cell viability systematically reduces. Well, this is some interesting aspect. The second point you can extract from the data is that if you make incubation short incubation, let's say 24 hours and 72 hours, and longer incubation of 72 hours, the toxicity increases as you increase the incubation time. So those are the two conclusions you can extract from the data. Of course, in the plots, symbols are the experimental data, and the solid black line are just straight lines linking the experimental points. So, although the experiment is very, very interesting, you cannot extract too much information from the data. And there is a huge missing of information behind this data if you do not perform a more precise analysis of the data. And this is one point of my talk. So let me briefly talk about the radiofrequency therapy. What is the instrumentation of this therapy? So on the right-hand side, you can see the system, the equipments typically used, which is the radio frequency generator. It can deliver hundreds of kilohertz, and you can control also the power delivered, let's say from 2 to 20 watts in power. And there is also, you need to close the circuit here, and that's why you use those two pads in the patient body. And on the other side, you have the electrode, And at the end of the electrode, you can see the detail on the central part of my slide. So here is the tip of the electrode, and then you have a needle, and the needle is inserted into the place where the tumor is. And on the left hand side, you can see a detail of the needle. So that is the radiofrequency electrode and the needle. And the needle goes into the tumor. And typically the tumor size is between 1 to 3 centimeter. And then you can emphasize important areas in the tumor. The blue area is the surgical margin, we call, and the red one is a sublethal area, which if you leave behind, there is a recurrence of the tumor. And inside the brown one is the lethal area, is the tumor itself. So, and then you can operate using several needles, like this left-hand side picture shows you. And in our particular experiment, we use about half megahertz, which is 500 kilohertz, and the power we delivered was about 5 watts. So here, of course, there is a heat when you operate the system. The needle, it actually it heats up, and then we need some cooling system. This is a standard cooling system for the electrode. So, and then there is a huge number of publications about radiofrequency therapy, and in general, after the radiofrequency therapy is applied to a tumor, there is a systematic reduction in the tumor size. In many cases, complete remission of the tumor. Now we want to combine the radiofrequency therapy with a nanocomposite. So this slide describes you what the nanocomposite is. The nanocomposite here is based on graphene oxide. So graphene oxide, and on top of graphene oxide, we deposit some gold nanoparticles, about 10 nanometers in size, and we coat the system with a polymer, which is polyethylenimine. So it's covered. And of course, we performed all characterization, materials characterization. For instance, in the middle, you can see a high resolution transmission electron microscopy of the gold nanoparticles. And it can emphasize the interplanar distance typical of gold, about 2.35 angstroms or 0.235 nanometers. On the right-hand side, you can see a result of the transmission electron microscopy of the nanocomposite itself. So the size, the typical size of the nanocomposite goes with this histogram. The mean size of the graphene oxide is about 27 nanometer. So we perform, besides this morphological characterization, we perform all kinds of characterization, including optical characterization of the nanocomposite, and also from the materials that comprise the nanocomposite. It means the graphene oxide, and the polymer itself, and the gold nanoparticle. So here is our in vitro experimental design. So actually in this experiment, we use two cell lines. One is the Walker 256, and the other one is the B16F10. So these two cell lines are typical cancer cell lines. So the first experiment, the two cell lines were incubated with the nanocomposite, increasing the concentration of the nanocomposite. In the second experiment, the same two cell lines were incubated with the nanocomposite, also increasing the concentration of nanocomposite. However, the radiofrequency therapy was applied. And finally, we collect all the data and we perform a mathematical analysis of the in vitro cell viability. So here is the mathematical model we used to describe the cell viability. It was based on the Hill model. I think it's worth mentioning that the Hill model was proposed more than a century ago. It was proposed in 1910 by the physiologist, the British physiologist Archibald Vivian Hill, and the paper he published, this was his second paper. And about 12 years later, this publication, Archibald Vivian Hill actually won the Nobel Prize in medicine and physiology. So, but here is the basic equation of the Hill model. It relates the cell viability as a function of the dose, which means the concentration of the challenging molecule. So the important points about this equation is the exponent that goes with the dose. That is the Hill coefficient. And this is a very important parameter, actually. Besides the Hill exponent, we have the K parameter, which is the decomposition of the complex between cell and the challenging material in terms of the that's the equilibrium constant for the composition of this complex. V naught and V1 are parameters that you have to fit, which are based on the scale of the data. So from this equation, you can find, for instance, not only you can extract the Hill coefficient and also the unbinding constant, but also you can, for instance, describe what we call the benchmark dose. The benchmark dose is typically the dose required to decrease the cell population by 10%. And also we can describe the lethal dose 50, which is the concentration of the challenging material required to reduce the cell viability by half, by 50%. And those are the equations describing the benchmark dose and the LD50. You can extract from the Hill equation. Now let me show you how was the data we extract from this experiment and the fitting of this data using this equation. So here is one of the cell lines. It's called Walker cell line, or LLC WRC cell line. Is a cancer cell line. On the upper plots, A and B panels, we have the cell viability as a function of the gold nanoparticles only. It's not the nanocomposite, it's the gold nanoparticle. On the left-hand side, without application of radiofrequency. On the right-hand side, the B panel is the toxicity of the gold nanoparticles after application of the radiofrequency by 3 minutes. So on the lower panels, C and D, we have the cell viability response on the nanocomposite, which is the graphene oxide, the polymer, and the gold nanoparticles. On the left, panel C is without application of radiofrequency. On the right-hand side, panel B is the application of the radiofrequency. You can see data which are quite different. For instance, C and D, if you look at the data, quite different. So the vertical columns are the experimental data, and the blue solid line is the best fitting of this data using the Hill model. So here is the second set of experiments, the B16F10 cell line. Again, the two plots on the upper side, A and B, represents the cytotoxicity of the gold nanoparticles for this cell line. So we have the cell viability reducing as a function of the concentration of the gold nanoparticles. Important to mention that gold nanoparticles are surface coated with citrate. But you can see on the left-hand side, without radiofrequency, on the right-hand side, panel B includes the application of radiofrequency. You can see the huge difference from one and another. Visibly, by naked eye, you can see the higher toxicity of the application after application of radio frequency. The point is, how high is this? So we can, if you look at the data only and try to extract some qualitative analysis of the data, you may say clearly that the radio frequency includes some extra cytotoxicity for this cell line, but how much you cannot say. Again, on the lower part of my slide, C and D are the cell viability as a function of the nanocomposite, increasing the concentration up to 50 milligram per ml. On the left-hand side, without application of radiofrequency. On the right-hand side, panel B is after the application of radiofrequency by 3 minutes. Remember, is half megahertz and 5 watts in power. But then, if you look at C and D, they are completely different results, showing that D is clearly has improved toxicity, cytotoxicity. And if you look at these four data, you may say, okay, so radiofrequency includes some extra cytotoxicity, but how much? So all the fittings, which represent by this solid blue line, I can collect all the data in this table, and that is going to be a little more clear how important it is to model the biological assays using any kind of mathematical model. So here in the table, we collect all the parameters of the Hue equation, V naught, V1, K, the Hue coefficient, the benchmark dose, and the lethal dose, LD50. So if you look at the Hue exponent here, just to remind you, the upper part of this table has to do with the Walker cell line, and the lower part of this table is the second cell line we use, the B16F10. So if you look at the data extracted from the Walker cell line, you see that the E exponent, the Hue exponent, are all over 1. And if you look at the second cell line, most of the data present the Hue exponent lower than 1. So actually 1 is a border, very important border for this kind of analysis. So if the Hue exponent is over 1, it means the first molecule or material that attached to the cell membrane just facilitates the next one to attach. On the other hand, if the Hue exponent or coefficient is less than 1, it means the first material that attached to the cell membrane just blocks the attaching of the next one. So it's a very important border then. And that is the first big difference between one cell line and the other cell line. So the two cell lines respond quite different from the same treatment. But if you look at inside each one of this cell line, for instance, on the Walker cell line, you may see that the Hue exponent changes dramatically without application with the gold nanoparticles without application of radio frequency, and with application of radio frequency, it's 1 order of magnitude higher. The Hue exponent after applying the radio frequency, which means radio frequency stimulates with 1 order of magnitude higher the binding of the gold nanoparticles in the cell membrane. Again, if you look at the data from the nanocomposite, the Hue exponent also changes at least 4 times. So without application of radio frequency, the Hue exponent is about 14, and with application of radio frequency, it drops down to 3. So the Hue exponent is very sensitive, not only to the kind of material you are using, but also whether or not you are applying radio frequency. The same pattern, the same trend you can see on the second cell line. So the gold nanoparticles alone provides you a Hue coefficient of about 3 without application of a radio frequency. However, if you apply radio frequency, it drops down 3 times, so it goes close to 1. Likewise, if you are using a nanocomposite without application of radio frequency, the Hue exponent is about 1. And if you apply radio frequency, it drops down to about 1/3. So, but if you look at the benchmark dose, which is the dose required to decrease the cell viability by 10%, there is a huge difference. So if you look at the column of the benchmark dose, which is rounded by blue and red, you can see that the gold nanoparticles has a benchmark dose of 1.3 micrograms per ml without application of radio frequency. When you apply that radio frequency, it drops down to 0.9. However, the huge and dramatic change you can see when you are using the nanocomposite. The benchmark dose of the nanocomposite for the Walker cell line is about 20 micrograms per ml if you don't apply the radio frequency. However, if you apply radio frequency, it drops dramatically 2 orders of magnitude to 0.08, which means it is about 100 times more toxic. So application of radio frequency turns the nanocomposite extremely toxic. If you look at the second cell line, the B16F10, it's even more, this cell line is even more sensitive to this treatment. So the gold nanoparticles without application of radio frequency, the benchmark dose about 0.5. However, if you apply a radio frequency, it drops down 3 orders of magnitude. It's a huge dropping. It becomes extremely toxic. But if you look at the nanocomposite for the same cell line, so the benchmark dose is 119 micrograms per ml. However, look at how much it drops when you apply radio frequency. So it drops to 5 orders of magnitude, extremely toxic. The combination of the nanocomposite with the radio frequency therapy for this cancer cell line. So we learn a lot looking at the data we extract from this table. And the same trend you can check on the lethal dose, the LD50. It follows the same trend. For instance, the LD50 for the second cell line is about 625 for the nanocomposite without application of radio frequency. However, if you apply radio frequency, it drops down to 0.2. So only by performing a mathematical analysis of the data, you can extract important information in a way which is reliable and you can extract the data and the associated standard deviation. Of course, I didn't plot here the standard deviation, but it is typical. So, and finally, let me conclude my talk. So the first conclusion is quantitative analysis does provide extraction of typical Hill coefficient, which is a very important point. As I said before, there is a border which is the Hill coefficient equals to 1, and we have data which has the Hill coefficient higher than 1 and less than 1 and lower than 1. And the second point is qualitative analysis does not provide extraction of nothing. Of course, you can extract some information looking at the data, but not too much. And actually is a huge missing of opportunity to learn from the in vitro assays. Moreover, quantitative analysis does provide extraction of typical benchmark dose and LD50, and qualitative analysis, no way. You cannot even guess with some precision what would be the benchmark dose or the LD50. It's very uncertainty, the data you can extract. And finally, quantitative analysis allows distinguish cell line bioresponse precisely. The data I show you in this talk show that the Walker cell line is less responsive of the treatment than the B16F10 cell line. So B16F10 cell line is much more sensitive to this treatment combination of the radiofrequency therapy and the use of nanocomposites based on graphene oxide, a polymer, polyethylenimine, and also small size gold nanoparticles, 10 nanometers in size. So finally, again, I would like to thanks again the organizers of this meeting and for the invitation to me to be here today and share with you the data. And also, I would like to thank all of you online attending my talk. If you want to contact me on the lower part of my slide, you can check my email address. And if you have any question, I'll be happy to take the question.
Thank you so much. It was a